Thanks for the introduction, Shaji. And yeah, like Shaji said, please feel free to stop me if you have any questions. So yeah, thanks for coming to my talk, everyone. In this talk, I'll present an overview of my recent ICLR paper in collaboration with Anders and Behnam and Google. And this is going to be about out of distribution generalization. So in the standard supervised learning setting, we imagine that the test and the training data are both drawn from the same distribution. But this is not really the case very often in practice. So for example, if your self-driving car model has been trained on images that were captured in some equatorial city, then you can expect that most of your data has been, most of your photos have been captured under really good daylight and really good weather. And very few data points might have poorer light conditions or foggy conditions and so on. At the same time, you would want to deploy these models across the whole globe. And so it's possible that you end up deploying this in a higher latitude city where you don't see as much daylight and you are very often faced with intense weather conditions which blur your vision. So in these situations, you would want your model to still be able to guarantee some good generalization. But this is not really the case in practice. Most of the training or most of the standard models that you train typically drastically deteriorate in performance when you see these kinds of distribution shifts. And you really want to solve them. And this work is about understanding why this sort of failure happens under this distribution shift. So one way to think about why this sort of failure happens is in terms of spurious correlations. So what are spurious correlations? So as one example of spurious correlations are backgrounds. So very often it happens that the backgrounds in these images happen to be correlated with the label during training. And that results in your model using signals from the background in order to make its decision. And this can often lead to surprising kinds of failure during testing. So as an example here is a picture of a husky, which a deep network ends up thinking is a wolf. And if you dig deeper into why it thinks it's a wolf, you would realize that the deep network is making use of the fact that there is snow in the background in order to classify that as a wolf. So essentially what's happened here is that in your training data, most huskies happen to occur in some indoor regions, and most wolves happen to occur in some snowy regions. So the model thinks if there is snow, it has to be a wolf. Another example of a spurious correlation is the one here, which is in a reinforcement learning setting. In the case of, here's an example from the Sonic the Hedgehog game, where you see that what you see in this image are regions in the image that have been highlighted, and the highlighted regions, which are sort of pinkish in color, and I'm trying to point that in with my cursor. But what these highlighted regions are essentially pixels that largely determine what your agent is going to do. And it turns out that the agent that you've trained somehow thinks that the scoreboard and the background are useful measures to determine what the actions are. And this is because for some reason during training, these signals are correlated with the correct action that the agent has to take. So this is like just to give you a high level, just to give you a concrete example of what spurious correlations are and how they can affect your test time performance. But let me go over a very simple illustrative example, which I'll use as a running example throughout the rest of my talk. So this is a cow-camel classification task. This is a standard example that many papers use to motivate this problem. So in this task, you imagine that you want to classify cows from camels. So imagine that you've drawn your training data from a particular country where the distributions of cows and camels look something like this. In particular, what you have are cows that are a majority of your data points are cows that occur in grasslands and camels that occur in a desert. And there is a minority of data points where this correlation is flipped, in the sense that there are some cows that are in a desert and some camels that are in a grassland. Now I'm going to imagine that you have a non-zero number of such cows and camels. And the reason I want to imagine that is because I'm creating a setting where the background is not fully correlated with the label, but it's weakly correlated. Like 85% of the time, the background is indicative of what the label is. That is, if you look at the grass, if it's grass, then you know it's a cow, and if it's desert, then you know it's a camel. And 15% of the time, it doesn't really tell you what the actual label is. So imagine you train your model on this sort of a data set, and then imagine testing your model in a data set that corresponds to some other country where, for some strange reason, cows like to be in deserts and camels like to be in grasslands. What happens here? You'd observe that your classifier that you trained on this, the data on top, ends up misclassifying all the data points here. It thinks that all the cows here are actually camels and all the camels here are actually cows. Or in other words, it's now using the background in order to primarily decide what the label is. And this is what I mean by the classifier failing under spurious correlations. Now, there have been many papers that have tried to resolve this problem. They've tried to come up with algorithms that somehow build models that do not rely on these spurious correlations. But in this talk, what I want to do is I want to dig deeper into why this happens in the first place. So why on earth do classifiers use the background, which is only weakly correlated with the label, even though the foreground information, that is the shape of the cow and the camel, is fully predictive of the label. So I want to understand this problem in more detail because that will be really crucial towards solving this problem better in the long run. Now, this is the running example, and I'm going to be using this in the rest of the talk. If there are any questions, please feel free to let me know, and I can clarify them at this point. Okay, so if there are no questions, let me give you an overview of what our results are. And this is going to be a very high-level overview. So basically, what we do is in this work, what we do is we take this existing theoretical model. So there is this existing theoretical model that tries to explain why classifiers use spurious correlations, and we ask whether that captures this phenomenon perfectly, whether that is the right way to think about this phenomenon. And we provide an answer that sort of suggests that it may not be the right way to think about this because it does not capture some of the fundamental reasons behind why classifiers use these spurious correlations. And I will describe what this model is in the next few slides, and I'll describe why it doesn't capture the fundamental reasons. But at a high level, what we do after that is we then move on to study a different theoretical model. We propose a different theoretical model, and within that model, we theoretically study linear classifiers, and we discover two new fundamental modes of failure. That is, two fundamental reasons behind why classifiers use spurious correlations. And while those insights are purely in a theoretical setting with linear classifiers, we'll then move on to empirically also verifying that intuition in the context of a deep learning set. So this is the high level outline. So what I'm going to do next is I'm going to spend quite a bit of time trying to explain what existing theoretical models, like the existing theoretical explanation for failure under spurious correlations, what that is, and why they may be inadequate. So in order to think about, so here's like a rough outline of what existing theory does. So it imagines that the training distribution looks something like this. So I'm imagining it in some 2 dimensions. So along the x-axis, let's say you have what I'm going to call as the invariant feature. These are also called as core features in some other papers, but at a high level, this corresponds to the foreground features, like the shape of the camel, the shape of the cow, and so on. And these are the features that you want your classifier to actually rely on. And along the y-axis, I'm going to think of that as the spurious feature. So these are features like the texture, like the background color, and other sort of spurious properties of the image that you don't want your classifier to use. Now, what existing theory does is it imagines that the data distribution looks something like this. So the data distribution is essentially something like two Gaussians that are overlapping. Now, what is important about this sort of a model is that both the spurious feature and the invariant feature are only partially predictive of the label. That is, I cannot just look at the invariant feature and determine what the label of the data point is. And I cannot just look at the spurious feature and determine what the label of the data point is. Now, in this setting, what will happen to the Bayes optimal classifier? Clearly, here, because of how the Gaussians overlap, you can sort of convince yourself that the Bayes optimal classifier has to look something like this, where it uses not only the invariant feature, but also the spurious feature. And that's because, like I said, the invariant feature cannot fully classify the data. So the spurious feature provides some extra information that's really crucial for increasing the accuracy of the classification. And this is basically the kind of story or narrative that existing theory has given in order to model this situation, in order to model why classifiers use the spurious feature. And in my work, like I said, I want to critically analyze this sort of a theoretical setup. And the reason behind why we're interested in it is that this model has been very useful. It has been useful for deriving a lot of new insights. It has been used to derive new algorithms for out-of-distribution generalization. It has been used to derive new synthetic data sets to play around with this problem. And people have also given many theoretical guarantees for these existing algorithms. And more generally, this has been useful for also reasoning about how spurious correlations affect the performance of the classifier. And because this sort of a theoretical model has sort of been taken for granted and been used in a lot of work, I think it's valuable to also make sure we understand the limits of this theoretical model. Now, to understand how this theoretical model is limited, one crucial observation is the following. In practice, you will observe that even when the invariant feature is fully predictive of the label, the classifier still relies on the background features, the spurious features, which are only partially predictive of the label. So this is like in the cow-camel example that I showed you like a few slides ago. There, the background was only 85% correlated with the label, but the shapes were 100% predictive of what the label is. And yet you would see that the classifier uses the background features. And unfortunately, this theoretical model cannot explain why this happens in practice. So to convince you as to why that's the case, let's imagine slightly tweaking this data distribution such that the invariant feature becomes fully predictive of the label. So for that, what I'm going to do is I'm going to reduce the invariance of the invariant feature. So these two distributions will become flatter and flatter. And then I'm also going to imagine how the Bayes optimal classifier will respond to that. So what you'll see is that in this sort of a Gaussian distribution setup, when I make the invariant feature fully predictive of the label, the Bayes optimal classifier will converge to the classifier that uses only the invariant feature. Or in other words, your classifier succeeds. It doesn't actually use the spurious correlation. So at a high level, what I'm trying to say here is that existing theory cannot tell me why. So existing theory has somehow constructed these tasks, which you can think of as somehow being deliberately difficult. So they've constructed these deliberately difficult tasks where the classes overlap. And because of the class overlap, you can explain why your classifier used the spurious feature. But then when there is no class overlap, this existing theory can no longer explain why the classifier still uses the spurious feature. So when the invariant feature is still fully predictive, it cannot explain why it uses the spurious feature. And that is what indicates that there should be a much simpler and much more fundamental reason as to why the classifiers that we use in practice rely on the spurious correlation. And in the rest of the talk, I'll go over what these fundamental sources of failure are. Sorry, is there any question about the motivation? Okay. So yeah. So the first failure mode that we identify is something that we call as statistical skews. So to understand this failure mode, let me start with a much simpler data set. So in this data set, what I have are data that are concentrated on 4 points. So there are 4 points in a square. Now, what are these 4 points? These 4 points correspond to the 4 different types of data points that you see in the cow-camel classification task. So in particular, along the first quadrant and the third quadrant, I have a majority of the data points. And these are the cows and camels in the correct background. And along the second and the fourth quadrant, I have a small number of data points where the cows and the camels are in the opposite backgrounds. Now this data set captures everything that I wanted to capture. In particular, it captures the fact that the spurious feature is only partially predictive of the label. This is because I have a non-zero number of minority data points. It means that I cannot just separate this data along the spurious feature axis. But at the same time, I also have that the invariant feature is fully predictive. This is because everything in the right side of the invariant feature axis I know is a cow, and everything that's in the left side of the invariant feature axis I know is a camel. So the invariant feature is fully predictive, and the spurious feature is only partially predictive. So if I can show that in this data set, for some reason, the classifiers use the spurious feature, then I'll be able to understand why, what the fundamental source of failure is. And to get there, I'm going to consider a linear classifier trained using logistic laws, which is like the most standard thing you would do on such a simple linearly separable data set. And we know that such a linear classifier would eventually converge to the max margin classifier. And this is something that some recent theory has shown, that such linear classifiers should converge to the max margin. So let me begin by looking at what the max margin classifier is going to look like in this setting. So my claim is that the max margin classifier will look something like this. So essentially, the max margin classifier succeeds. It uses only the invariant feature to make its decision, and it doesn't use the spurious feature at all. And the reason is that you have at least one data point in each of the corners of in each of these quadrants. So there is no reason why you can maximize the margin by using also the spurious feature. So there's no incentive for this max margin classifier to use the spurious feature. But surprisingly, what happens when you train gradient descent? So when you take the linear classifier and train it using gradient descent, like I said, we know that it converges to the max margin classifier eventually when given infinite time. But what you would see in practice is that when you have a lot of spurious correlation in your data, the finite time trained gradient descent classifier still relies on the spurious feature. So even though it's eventually supposed to get rid of this dependence, eventually it's supposed to converge to the max margin classifier. In practice, when you train it even after a long time, you'll observe that it still uses the spurious feature. So this suggests that there is something to do with finite time gradient descent, which causes the classifier to fail in this setting. And I want to know what that is. So
Is there a question? There's a question in the chat, yes.
Yeah, sure.
In the motivation slide, when you say that the model does not only use the invariant features, even when it is fully predictive, do you say this is based on empirical evidence, or do you mean the weights linked to the spurious features are still non-zero?
So this is based on empirical evidence. That's a good question. So we test this in practice by on some synthetic data sets and also some both synthetic and really toy data sets like the one I'm showing you here. And based on that, we were able to conclude that even when the spurious feature is only weakly predictive of the label, and when the invariant feature is fully predictive of the label, you see that in practice, classifiers use the spurious feature.
Okay.
Okay. Sorry, just give me a moment. So how do we? So in order to understand why finite time gradient descent fails here, we perform a theoretical analysis, which leads us to the following theorem, where we show that for a large class of linearly separable data sets, so by which I mean it's not just this simple toy data set, which is in 2 dimensions, even in data sets where your invariant feature is in higher dimensions. So in a much more general class of data sets, you can show that the spurious component in your classifier, which I'm denoting by WSP, at time t. So I'm looking at gradient descent as a function of time, as a function of the number of time steps. And so the spurious component divided by the invariant component. So I'm imagining that the invariant feature can potentially be high dimensional here. So this ratio is determined by this quantity, which is proportional to how much spurious correlation you have in your data set divided by log t. Now let me try to unpack what this theorem is trying to say. So let's look at the numerator here. So what this numerator tells me is that when t goes to infinity, this quantity will become 0, which makes sense because, like I said, when t goes to infinity, you get to the max margin classifier, and the max margin classifier does not use the spurious feature. And what's more interesting here is that this is a very slow convergence rate. So the denominator here is not a t or a t square, which is what you would expect for some reasonable level of rate of convergence, but this is a log t. So if I want to reduce the spurious component in the classifier by a factor of 10, then I have to wait e to the power of 10 many time steps in order to get there. And this explains why in practice, even after a very long time of running gradient descent, I do not observe that the gradient descent classifier has converged to the max margin classifier. It still uses the spurious feature because of this reason. And it's worth noting that this result builds on an existing convergence rate, which was given to be 1 over log t, but that was a rate that was independent of the distribution. It was in some sense a worst case rate. And it doesn't tell me how the spurious component of the classifier evolves as a function of the level of spurious correlation in the data set. So in particular, what is particularly interesting about this bound is the numerator. So what the numerator tells me is that depending on how much spurious correlation I have in my data set, so if, for example, if my data set has a really large level of spurious correlation, then then for a fixed point of time t, I'll have a greater level of spurious component in my classifier. And if I don't have much spurious correlation in my data set, then my spurious component will also be proportionally much smaller. And so this is essentially what the result is trying to say. I'm not going to give you the mathematical expression for what I mean by the level of spurious correlation because it's a pretty cumbersome mathematical expression. But yeah, at a high level, it's just a quantity that determines how much the spurious feature correlates with the label. So if I lost you there, what I'm trying, like the high level message of this theorem is what this is trying to say is that even in data sets where the invariant feature is fully predictive of the label, you can show that gradient descent trained classifiers fail. And that's because of some weird sort of bias in finite time gradient descent, and essentially the skew in the ratio between the minority group and the majority group, and which is essentially skew in the statistics of these two groups. So this is the first failure mode. The other failure mode is a much different failure mode that we come up with, and it has to do something with the geometry of the data set. So let me explain what that is. So let's go back to this data set with just 4 data points and recall that the max margin classifier here succeeds. So it might be tempting to think, so does the max margin classifier always work? So does the max margin classifier always rely only on the invariant feature? Unfortunately, the answer is no. In fact, in most real world data, where the geometry of the data set is much more non-trivial than what I've shown you here, you can show that even the max margin classifier is going to fail. Like even that is going to look like some sort of a diagonal. So in the next few slides, I'm going to show you what that non-degenerate geometry is. Like what is the geometry in the real world data that causes even max margin classifiers to fail? So recall that in the previous example, if I were to focus only on the invariant feature, it's going to all be collapsed in just 2 data points. But in the real world, it's reasonable to imagine that the distribution of the invariant feature looks a lot more interesting. It's going to have a lot more diversity. You're not going to see the same cow shape and the same camel shape again and again. It's going to be spread out and it'll look something like this. And this leads to a very crucial property about the geometry of these data points. In particular, as I sample more and more data, the margin of separation along the invariant feature is going to get smaller and smaller. And, or in other words, to sort of summarize what I just said, if you were to plot what I'm calling as the invariant margin. So if you were to plot the margin of separation along the invariant feature as a function of the number of training data, in the real world, you'll see a graph that looks like this. And this is something we'll empirically verify in a few slides from now. But for now, just trust me that this is true. And in the next few slides, I'll show you how this sort of property can be used to understand why even the max margin classifier is going to fail, is going to use the spurious feature. I guess this is a good point to make sure everyone is on the same page as me. Okay, if there are no more questions. So why does this help? So like I said, this observation is crucial towards helping towards understanding why the max margin classifier uses these spurious correlations. And for that, we have the following result about max margin classifiers, which is something like this. So imagine that the total norm of the classifier is 1. So I'm just looking at the spurious component, the magnitude of the spurious component in the classifier. And then what this result says is that this component can be related to how fast this graph decreases. So the faster this graph decreases, there's going to be a larger spurious component. Now I'll give you this might be a bit vague and like it might not be clear what exactly this formula is, and I'll give you a sense of what that formula is in a few slides from now. But let me first make sure that this intuitively makes sense. So as a sanity check, let's go back to the 4-point data set where we know that the max margin classifier is going to succeed and it's not going to use the spurious feature. And fortunately, this theorem does verify that fact. Like it's consistent with that fact. What this says is that in this particular data set, because all your data points are concentrated on just 2 points in the support, recall that as I sample more data points, the invariant margin is going to not decrease. The margin of separation is not going to decrease. So in this case, the graph is flat, which means the rate of decrease is 0, and therefore the spurious component is 0. So we know that this theorem makes sense in this really simple setting. Now, what happens in a more realistic setting where I said the distribution looks something like this, where the invariant features are going to be more spread out? Now here, like I said, we know that the margin of separation is going to decrease as I have more data. So what this theorem says is that there is going to be some positive rate of decrease, and therefore the spurious component is also going to be non-zero. So that's why this is what I mean when I say that this theorem explains why the classifier uses the spurious feature. And now I'll try to explain the intuition behind why this is the case. So to understand why this is the case, let's imagine what happens when I sample a finite set of data points from this sort of a distribution. The data points will look something like this, where along the first and the third quadrant, because I have a majority of the data points, I'm going to end up sampling too many data points from those quadrants. And along the second and the fourth quadrant, because I only have a minority of data points, I'm going to sample very few data points from there. But more crucially, what is also important is the geometry of what these quadrants, what these data points is going to look like. In particular, along the first and the third quadrant, because I have a lot of data points, the margin of separation is going to be very, very small because I sample more and more difficult data points, and they'll get much, much closer to the, very, very close to the separation boundary. At the same time, along the second and the fourth quadrant, because I've sampled very few data points, the margin of separation is going to be really large. So all in all, what's happening here is that I end up having a lot of empty space in the second and the fourth quadrant. So if you were to ask a classifier to maximize its margins, it's naturally going to take advantage of that empty space. So it's going to, in other words, it's going to use the spurious feature in order to maximize its margin. And crucial to that is the fact that there is this sort of weird imbalance in how the margin of separations look like in all these quadrants. And now let's look at this a bit more mathematically. What we show is a theorem that looks something like this. This has been extremely diluted. The theorem is has a lot more details to it. But at a way, what this theorem is trying to say is that the spurious component can be lower bounded in terms of two quantities. So the first quantity here, which I am referring to as gamma minority, refers to how much separation you have in the minority groups, how much margin of separation you have. And the top quantity here, which is the gamma majority, is how much separation I see in the majority group, which is going to be very tiny. So now recall that this graph, this invariant margin graph, is going to decrease at some rate. So we know from this graph that the margin of the majority group, which has a lot of data points, is going to be much, much smaller than the margin of the minority group. So when the graph decreases at a faster rate, there'll be a much larger gap between these two margins. And when there is a much larger gap between these two margins, you can show that the lower bound on the spurious component here is much, much larger. And therefore, when the graph decreases faster, you can show that this classifier uses the spurious number more prominently. Are there any clarification questions about the proof? Okay, so yeah, so let's take a step back, and at a high level, what we've seen here is that, again, when we still are in a setting where the invariant feature is fully predictive of the label, and we are able to show that even the max margin classifier can fail in the setting. And this is because of something that has to do with the geometry of the data points, and also the fact that you want to maximize your margin. So to recap, I think it's helpful to sort of differentiate these two failure modes. So we saw that there's this failure mode due to something called a statistical skews, and we saw this other failure mode due to geometric skews. So but these are two very complementary kinds of failure modes. And the reason they're complementary is because the statistical skews failure mode is something that we saw can happen even in a very simple data set where all your data points are collapsed into few points in the subcode. And at the same time, it occurs only due to some sort of bias in finite time gradient descent. But if you were to train finite time gradient descent to an infinite time, this particular failure mode will stop affecting the performance because it will converge to the max margin classifier. But at the same time, if your data had some interesting geometry, which is often the case in the real world, like I'll verify soon, you will see another kind of failure mode. And this failure mode will occur in any margin maximizing classifier. So we saw this for the max margin classifier in particular, but even for finite time gradient descent, because it's maximizing some notion of margin, you should be able to intuitively show that even that is going to be biased due to these weird geometric skews. So now the last part of this work is to also verify some of these insights in practice, which I'll just try to quickly summarize them. But yeah, so like I said, most of the theory is concerned with linear classifiers, but we want to test these in neural network settings on data sets like MNIST and CPARTET. So in order to verify the statistical skews, we design the following experiment. So what we do is we take a control data set which has no spurious correlation. So imagine this is a data set where cows and camels are equally likely to be in both the desert and grasslands. And then what we'll do is we'll merely duplicate a subset of these points to create an experimental data set where you do have spurious correlation. So I'll take the camels in the grasslands and camels in the desert and cows in the grasslands, and I'll duplicate them like 10 times. So that'll artificially create a spurious correlation between the background and the label. Now, the interesting thing about this sort of a setup is that the control data set doesn't really have any sort of skews. Because the proportion between the two sets of data points is the same, you'll neither have the geometric skew nor the statistical skew. On the other hand, in the experimental data set, because I merely duplicated a bunch of data points, you're not going to have any geometric skew because I don't really mess around with the geometry of the data set. But then I am introducing a statistical skew because the proportion of majority points is going to be much larger than the proportion of minority points. Now, what I'm going to do is, in these kinds of data sets, I'm going to train a gradient descent, a neural network using gradient descent on both the control data set, which is given by this black line on top, and also on the experimental data set, given by the blue line over here. And then I'm going to vary the spurious feature during testing, and I'm going to see how the accuracy of the classifier drops. And what we see is that the neural networks that are trained on a control data set, which without any geometric or statistical skews, are fairly robust much more robust than robust to these shifts in the spurious feature than the classifiers that have been trained on this experimental data set where you have these statistical skews. So yeah, so what I plotted here are the accuracy. So lower values means lower accuracy. So yeah, so this gap over here is one way to verify that gradient descent training on neural networks is still going to be susceptible to these kinds of statistical skews. And it's not just something that linear classifiers suffer from. We also try to verify geometric skews. And here recall that the fundamental premise was that the margin in real world data, the margin of separation decreases with the number of training data points. And one sort of way to determine that this is true is to look at the norms of your classifier. So for example, in the case of a max margin classifier, that's an SVM on random features. So these are features that I don't actually train. So I just embed the data points in some high dimensional space, and then I train a max margin classifier on that. So I'm training this max margin classifier to achieve a margin of 1. So in other words, the L2 norm of the classifier is equal to 1 over the margin of separation of the two data points. So if I can show that the L2 norm increases with the number of training data points, it's as good as showing that the margin of separation decreases with the number of training data points. And in this case, I do observe that the L2 norm increases with the number of training data. Now, of course, that is on the max margin classifier. What happens in the case of neural networks? So here things are much more fuzzy. We don't really have a good understanding of how the margin of separation relates to some sort of norm of the neural network. So as a surrogate for that, we just look at distance from initialization. And what we see is that as you add more and more training data, you definitely require a lot more norm in your distance from initialization in your deep network in order to classify that training data. And intuitively, this is true because as you have more training data, you have you add more and more difficult data points. So the classifier has to like use much more weight norms in order to classify the data points. So I want to quickly outline a particular theoretical aspect of our work, which is that we develop this, and this is something that I'm not discussed in the talk, but yeah, this is just going to be brief. So what we do is we develop this theoretical framework of what we call as easy to learn tasks. So these are tasks where the setting is designed to be easy for the classifier to work successfully. So for example, these are tasks where the invariant feature is fully informative of the label. And what we do is we show that in these tasks, even in these easy tasks, classifiers can fail due to geometric and statistical skews. And that's important to show because this implies that our insights are general. So in other words, if I can show that even in such really easy tasks, a classifier is going to fail, it means that even in much harder tasks, classifiers could fail for the same reason. It could fail for even other reasons in those harder tasks, but what we can say is that these sort of statistical and geometric skews, because they occur even in easy tasks, they will also occur in much more general, harder tasks. So in that sense, our insights are general. We also show that in some sense, these kinds of, as far as these easy tasks are concerned, these skews that we saw are necessary and sufficient for failure. So in other words, in these easy tasks, there are no other such failure modes. And this would be of theoretical interest. And we also go beyond all of this to enumerate a few other such failure modes, that is, few other reasons why classifiers use spurious features in a range of other harder tasks. Now, these sort of failure modes are not as general, or they are not as fundamental as the geometric and statistical failure modes, but they are still very valuable to know because in practice, you would still see these kinds of failure happening. So yeah, so to summarize, we provide this theoretical framework, and what's useful about this framework is that it comes up with a minimal set of tasks. So if you were to propose a new out of distribution generalization algorithm, you should hope that it solves this problem, at least in this particular set of easy tasks. So this brings me to the end of the talk. So to summarize what we saw, we sort of critically analyzed this existing theoretical model as to why classifiers use spurious features. And we proposed an alternative model where we were able to come up with two distinct ways in which classifiers use spurious features. And hopefully this can give us newer insights and potentially more, this gives us a much more appropriate theoretical model on which we can build new algorithms and build new theory in the long run. And there are definitely many exciting directions for future work here. So for example, we only briefly looked at these other kinds of failure modes, and I think understanding them more deeply would be very valuable. For example, are there certain kinds of failure modes which do not really occur in linear classifiers, but can occur in how deep representations are learned? Or to be clearer, like the kind of failure modes that I described are failure modes that occur even in linear classifiers, but it's possible that deep representations are learned in a way that introduces other kinds of vulnerabilities. So what are those vulnerabilities? Another more practically important question here is, there are some general purpose out of distribution algorithms. Could we potentially try to specialize them to the kinds of skews? Like, can they take advantage of the knowledge that we have about these skews in order to improve their performance? And I think a much more broader and fundamental question here is to understand what sort of distribution shifts happen in practice. Like, what are spurious features and how can they manifest in the real world? Are backgrounds the only way spurious features backgrounds and texture, are they the only kinds of spurious features we see, or are there other kinds as well? And I think understanding this will be really crucial for us to develop a basic framework to think about out of distribution generalization, and to also develop theoretically sound solution techniques for it. So yeah, that was all my talk. Thank you so much for coming to my talk. And this is the paper that I gave an overview of. Please feel free to check it out, and also email me if you have any questions, or you can even ask any questions if you have right now, and I'll be happy to answer. Thanks for coming.
Okay, are there any questions from the audience? Okay, maybe I'll start with one. Yeah, so I think you've been mostly talking about the binary classification case, right? Like let's say camel versus cows. But let's say if today there are images with, let's say fox on desert and also sheep on grass. So basically there are, multiple classes. Do you think that will make the problem more serious or less serious? And how that would affect this out of distribution generalization problem?
I definitely think it should make it more complicated. But I can also imagine situations where, so for example, in our paper, we were able to at least come up with a synthetic task where if you're, in the case of CFAR 10, you have 10 classes, right? So if you can somehow introduce a spurious feature that is unique to each class, then your classifier does end up picking up those kinds of spurious features. But in practice, it's probably not the case that there's a spurious feature that's unique to each task. But I definitely think that you would still face these kinds of problems. So for example, if two classes share the same kinds of spurious feature, then it's possible that the classifier still sort of gives more weight to those classes when it sees those spurious features in your training data.
Okay. No, I guess what I was thinking is, okay, if the model sees there are sheep on grass and cows on grass, maybe other animals on grass, then wouldn't it start to realize that grass is a feature that, that it doesn't want to use to make predictions?
Yeah, okay, yeah, I can see what you're saying. In that case, yes. In that case, I think it would be relatively less. It will be a bit more benign, but you can still imagine, for example, let's say you never see lions in grass, but you see sheeps and sheeps and cows in grass. And in your test data set, you end up seeing a lion in grass. So it's possible that the classifier still thinks if it's grass, then it's one out of sheep or cow or whatever the other grass animal is. So in that case, you could still expect some sort of failure.
Okay.
But yeah, that's an interesting question.
Yeah, and which makes me further think about, whether this kind of like what this phenomenon would be in, let's say, not supervised settings, right? Like in the cases where, if there is no label, does it mean this problem doesn't exist, or does it exist in some other forms?
That's an interesting question. So, I mean, in the case of, let's say you have a generative model and you're training it on this cow camel data set, it's of course going to learn a data set that reflects the same kinds of spurious correlations, which is technically the right thing it's supposed to do. It's supposed to generate cows that are mostly in grasslands and camels in desert. But if you care about getting rid of these spurious correlations, then you have to do something. Like if you want a more diverse data set, which has equal proportion between all these kinds of data points, then you would have to definitely do something much more clever.
Right, that makes sense. Okay. Any other questions from anyone in the audience? You can also feel free to ask, feel free to email Vaishnavh, I believe, if you want to chat more about this.
Yeah, for sure.
Hi, thanks for the presentation. I was curious if you've considered how your explanation versus the de facto explanation apply in the adversarial case versus sort of a spurious correlation case, right? So when you've got an adversary effectively intentionally generating the spurious use cases.
So I guess I should clarify. Okay, I'm trying to understand what sort of an adversary you're imagining here. So in throughout this whole discussion, I'm imagining that the adversary generates the test data, and in the test data, the spurious correlation is completely flipped. So in that kind of setting where the adversary flips the correlation completely during test time, there our model captures fundamental failure modes when compared to existing work. But perhaps I didn't understand what sort of an adversary you're imagining.
Yeah, I mean, so the adversary is essentially trying to key in on the spurious differences, like that the max margin classifier would be generating, right? So he's trying to identify the spurious mistakes that a classifier is making and exploit them.
I see. Yeah. So if I understand your question correctly, like the setting we are considering is an adversarial setting, and in that setting, the kind of failure that we demonstrate is more fundamental than the existing standard model. But yeah, I might not be understanding the question completely. So I would definitely love to hear more about this over email.
Okay, thanks.
Yeah.
Any other questions?
Yes, hi.
Hi.
Hi. Thank you very much for this very nice, very clear presentation.
Thanks.
So I'm coming from neuroscience and the visual system.
Oh, I see. Okay.
And actually the type of spurious example you were talking about, especially from an object being different from the background and from the kind of the natural statistics from which the object should be coming from. So it reminds me a lot of the work of Di Carlo at MIT, where they actually have databases of objects and they randomize the background. And their whole approach is actually not to consider these examples of spurious, but actually as how the brain and deep learning models can achieve invariance instead. So have you considered this other way of looking at this problem, that the lack of invariance recognition?
Yeah, so our work was in fact inspired by like some recent work on capturing these kinds of invariances. And there's also this invariant risk minimization paradigm, which people have proposed to solve this. But yeah, we haven't really thought about how to resolve these problems, like how to fix this problem. Like it's an ongoing work. And yeah, in that context, I think it'll be very useful to think about such invariance-based approaches. But yeah, the purpose of this work was to, as a first step, try to understand why this failure happens in the first place. But yeah, when it comes to solving it, I think capturing what features are like invariant across these domains is definitely the way to go, and definitely making use of like causality and ideas from there would also be very useful.
Great.
Yeah.
Thank you. Have you considered just models where you try to extract the object even if it's not perfect, or try to dissociate dissociate different elements of the image?
Yeah, I haven't done it. Like I said, I haven't actually yet tried to solve this problem. But I think people have definitely tried that. I can share some references over email. But yeah, people have tried this, and then there's also been a recent work where they generated data sets. I'm not sure if you were referring to the same work, by the way, but yeah, they generated data sets where they sort of extract the object, and then they tested how these models behave when trained on the extracted object, and they did show improvements in terms of how much they rely on the spurious feature. So yeah, definitely, I think that's a promising direction.
Okay, great, thank you.
Yeah.
Any other comments, questions?
I think someone raised their hand.
Oh.
I don't know if they had a question.
Where?
Can you hear me now?
Oh, yeah.
Yeah, sorry, I had my mic off. So I'm going to ask an incredibly naive question, but it's one that keeps coming up, so I regret not asking it. But the role of regularization in this whole thing, right? I mean, so in the two-dimensional simple setting, perhaps in part because it's so simple, I think any practitioner would say, oh, well, you're going to solve that with maybe not lasso, because that's kind of, it's going to pick up some of this spurious correlation, but, you know, it's not going to be as bad. But I imagine that certainly with something like a neural net, with the more dimensions that you can get a spurious correlation, you'd have more issues. So I'm kind of like 50-50 how stupid of a question is to ask about regulation here, but I feel like that's something that should be commented on, right? So if you could, what's your take on where it might fail, or if this is all just something that someone who's using regularization shouldn't care about?
Yeah, so I think, yeah, that's definitely something, that's a good question that I should have addressed. So in the case of, in the 2D setting, for sure, I think you can come up with some regularization technique that can circumvent these issues. So for example, you can add some L2 norm regularizer, or you can like you can sort of increase the learning rate over time as a form of speeding up the convergence rate to the max margin, and that would get rid of the effect of these statistical skews. You could also imagine, let's say you know that the invariant feature is feature 1 and the spurious feature is feature 2. Then you can imagine applying some sort of feature selection method or some L1 regularization. And I think in that case, it should figure out that the first feature is the one that you should be using. So yeah, I think in these 2D cases, you can come up with some simple regularization terms that could solve this problem. But yeah, in a more general situation, and definitely in the case of neural networks, I don't think a simple form of regularization is going to resolve any of this. And the way that people typically try to address this is by imagining that you have data that comes from different domains with varying levels of spurious correlation. And by somehow enforcing some sort of like invariance across these domains, like by enforcing that the representation in one domain is very similar to the representation in another domain. By applying such cross-domain penalties, people have proposed algorithms that work for neural networks. I mean, but we still haven't really reasonably solved it, I think. But yeah, in neural network settings and in settings where you don't really know that the first feature is the invariant feature and the second feature is the spurious feature, I think things get a lot more complicated, and simple regularization techniques are not going to help. Did that answer your question?
Yeah, that did. Thank you.
Okay, awesome.
All right. I think we're kind of running out of time. If there's no more questions or comments, let's thank Vaishnavh again for this amazing talk. So
yeah,
just as a reminder, we're meeting again at the same time next week when we're going to have Kayvon Fatahalian from Stanford University talking about some challenges in recent progress in making model training efficient and interactive. Well, thank everyone, and especially Vaishnavh for attending the seminar today.
Yeah, thanks, Shaji, and thanks for coming, everyone. And please feel free to email me. There was definitely one question that I wasn't able to resolve. So if you can email me, that would be great.
All right.
Yeah.
Cool.